Weather impacts each of us just about every day. In this video lecture, we will take a closer look at the terms heat and temperature as we begin to build an understanding of how major weather systems work on planet Earth. To begin, let's think about energy. It takes energy to make clouds, rain, and storms. Where do you think this energy comes from? If you guessed the sun, great job. The sun is the ultimate driver of all weather on planet Earth. And because different portions of the planet receive different amounts of energy in the form of heat, the Earth's atmosphere is constantly at work trying to achieve some type of equilibrium between the cold polar regions and the warm equatorials. This transfer of heat is the ultimate driver of all weather on Earth. So to understand weather, we need to understand heat. And to begin, heat is energy. To be more specific, heat refers to the total amount of kinetic energy of all of the molecules in a substance. So here we have a bunch of molecules moving around a little bit, and if you sum up all of that energy of motion, that is to say, that is the heat. And it turns out that even solid cold objects like ice still have some energy of motion. It's just that the molecules in that substance would be moving more slowly than something like, say, a gas, which has a very high amount of motion. And if you sum up all of the motion of those gas particles, you would have a significant amount of heat energy. This does beg the question, what is temperature? Well, if heat is the sum total of all of the kinetic energy of all of the molecules in a substance, then temperature is the average of all of that energy. For example, it's possible for something to have a lot of heat but a very low temperature if all of the energy is spread out over many, many molecules. Okay, time to check our understanding. Consider two identical pots sitting on a stove. Each holds some water. However, pot B holds twice as much water as pot A. At time t equals 0, the burners are turned on. After 1 minute, what can we say about the temperature of the two pots? A, pot A has higher temperature. B, pot B has higher temperature. C, the two pots have the same temperature. If you said pot A was the one with the higher temperature, great job. This time, same situation. This time we turn the burners on, and after 1 minute, what can we say about the amount of heat in the two pots? Does pot A have more heat, pot B have more heat, or do the two pots have the same amount of heat? If you said C, they have the same amount of heat, great job. These are identical burners. You turn those burners on, you start sending heat energy into the system. You're going to send the exact same amount of heat in. The only difference is that pot A has less molecules it has to share that heat with, so the amount of energy per molecule is greater, and so it has a higher temperature. Okay. Now that we understand the difference between heat and temperature, and because we recognize that atmospheric processes are driven by heat transfers, let's think about what actually happens when we add or remove heat to or from a substance. Basically, there are two options. Heat can either go into heating up a substance, or it can go into changing the phase of a substance, for example, from liquid water to water vapor. The term specific heat refers to the amount of energy required to raise the temperature of a substance. So anytime that heat goes into a temperature change, we can refer to that as specific heat. Latent heat, on the other hand, refers to the amount of heat taken in or given off by a phase change, a change from, say, a solid to a liquid, or a liquid to a gas, or a gas to a liquid, etc. Now, Different substances, as you might imagine, have different specific heats. So on a sunny day, rocks on the ground are going to heat up fairly quickly because they have a fairly low specific heat. Water, on the other hand, compared to most substances on the planet, has a very high specific heat, meaning it's going to take a lot of energy for that water to change temperature. And this is why lake water typically doesn't warm up until the end of summer, even though our rocks on the ground over here can get quite hot over just the course of a single day. Of course, this doesn't only apply to heating things up. You can also think of it in reverse and let cooling happen as well. And those same rocks that heat up rapidly over the course of a single day are going to release all of that heat back into the atmosphere within just a few hours of sunset, while the lake is going to take months to cool back down again. During a phase change, however, none of the heat being added to or removed from the sample goes into changing the temperature of the substance. Instead, it all goes into breaking or forming molecular bonds. For example, to melt ice, the water molecules need to absorb enough heat energy to break the bonds that allow it to exist as ice. The amount of heat that the ice must absorb is called the latent heat. On the other hand, if you wanted to take some liquid water and freeze it, you would actually have to remove heat from the substance. In this case, the amount of heat that you need to remove to result in that phase change is again called the latent heat. Of course, energy is neither created nor destroyed. It has to come from somewhere. For ice to melt, it has to take heat, energy from the environment, and that will enable it to melt. And for the liquid water to evaporate, again, it has to absorb heat energy from the environment and able to melt. However, on the other hand, when water condenses into a liquid, it's going to need to dump that heat energy back out into the environment. And same thing, in order for that liquid water to freeze, it has to dump heat energy in the form of latent heat out into the environment. Okay, time to test ourselves again. In general, which material will heat up faster, the rocks on the land or the water in the sea? Rocks on the land. Good job. Which material is able to retain its heat energy the longest, the rocks on the land or the water in the sea? The answer is B. The water in the sea is going to hold onto that heat energy the longest because it has such a high specific heat. It takes a lot of energy transfer to change temperature, even by a single degree. When ice changes to liquid water, it A, absorbs heat energy, or B, releases heat energy. To melt ice, you need to absorb heat energy. We call this melting. If I was to give you a bag of ice and ask you to melt it, you might take it over to your stove, turn the burner on, add heat to the system. That heat will go into those water molecules, and you will end up melting the ice. When liquid water changes to water vapor, does it A, absorb heat energy, or B, release heat energy? If I asked you to take a bunch of liquid water and turn it into vapor, you would probably head back to that stove and provide more heat energy to the system, enabling those water molecules to absorb heat energy. And this process is, of course, called evaporation. Final question. When water vapor changes to liquid water, it A, absorbs heat energy, or B, releases heat energy? In order to get a vapor, which has a lot of energy, to be a liquid, you're going to have to remove some of that heat energy. So taking a water vapor and turning it into a liquid is actually going to release heat into the surroundings. And of course, the term for this phase change is condensation. At this point, hopefully you are beginning to see how each of the concepts shown is crucial to understanding how heat energy is transported through our atmosphere, which ultimately will help us to understand at the macroscopic level the temperature and precipitation patterns of the entire globe. This concludes this video lecture.